Greetings everybody. So right now I'd like to make a video to elaborate a little more about some basic facts for the normal distribution. I have already made an introductory video on that with some basic information about what the normal distribution is, but I'll go into a little bit more detail about that in this video and show you some examples from MyMathLab. So what you're looking at here is the graph of a normal distribution. This is what it looks like. I'll elaborate a little bit more on how this can tell us something about data, okay, in a little while, but for now I just want you to look at this graph and think about some of the properties for it, okay? So for the normal distribution, right now we're looking at it. It has a mean of mu, so that's a Greek letter right here, mu, and a standard deviation of sigma. I'm telling you that just so you know what those symbols mean when you see them. Okay, sigma the standard deviation, mu the mean. Okay, the normal distribution is bell-shaped. Okay, and it is symmetric about the mean. And what I mean by that is that if I were to draw a line right down the middle where the mean is, then it's a mirror image of itself on either side. And what I mean is it looks identical on either side. All right. The shape of the curve on the right of the mean is not really any different than the shape on the left. Okay, there are lots of ways I could describe the symmetry of it, but that's probably enough for you, so I'll leave it at that. Another thing is that notice how the curve slopes downward and then it kind of levels out right here. You see that? So it does not cross the x-axis or the horizontal axis. It kind of just curve down towards it and never quite touches it, just getting ever closer and closer. All right. Okay. Now another thing is that for data that has a normal distribution, or for the curve of the normal distribution, virtually all the curve is within 3 standard deviations of the mean. So here's the mean. This is 1 standard deviation up, 2 standard deviations up, 3 standard deviations up. So we've got almost all of the right side of it within 3 standard deviations. And you can take the mean, you can go 1 standard deviation down, 2 down, and 3 down. You've got virtually all the curve existing either above or below 3 standard deviations of the mean. Okay. Now I can be a little more precise about that. It turns out that it's a matter of fact that 68% of the curve or the data is within 1 standard deviation of the mean, 95% is within 2, and 99.7 is within 3. So if I say virtually all the curve is within 3 standard deviations of the mean, I mean 99.7% of it is within 3. Another way that it's sometimes described is that these points on the curve called inflection points occur or mark 1 standard deviation above the mean and below it. Now inflection points, I guess, is somewhat of a technical thing, but it's the point where the curve transitions from sloping upwards to sloping downwards. You gotta think about the curves going up, and at some point it starts turning down. The inflection points is where it makes that change. So curve going up, and then right here it gradually starts going down, okay, falling on the other side. On the other side it's going down, and then it's gradually starts sloping up, okay? So that's how the inflection points are described. It's where the curve's changing direction. But I might also say that, sure, this is a curve, it's not a straight line, but this little section right here is roughly straight. Like if you just look at this, that part of it doesn't look curved. And over here, same thing. This part of it doesn't look curved. Yeah, up there it does, and down here it does, but this part right there doesn't. And I mean, I guess if you look roughly in the middle of that, we'll find the inflection points, which mark off 1 standard deviation under the mean and 1 standard deviation above it. Okay. So let's see an example. You know, a normal distribution, a normal curve, they can all look very different though. You know, it's like this is in general what they look like, but different normal curves for different data can look very different. So here's 3 normal curves right here, okay? Curve A, curve B, and curve C. And they all have these properties I mentioned here they're bell-shaped, they're symmetric about the mean. You know, the mean's right in the middle. They don't cross the x-axis, and so on. They've got all those properties, but curve A is very narrow and tall. Curve C is much wider, and curve B is kind of in between. So it says here, which if we were to look at these and we can accept that they're all normal, which curve has the greatest mean? Well, the mean is right in the middle of the curve, right? And so, like here with curves A and C, they look like they have the same mean actually, of about 45. Like that's where if this is 40 and that's 50, the middle of both curves A and C looks to be about 45. Okay, so I'd say they have a mean of about 45. But B is like shifted further to the right. You know, in the middle looks to be a little more than 60. So, you know, B has the greatest mean. It has the middle of it is a bigger number. It's the biggest of all of them. Next, which curve has the greatest standard deviation? Well, we can think that the standard deviation is a measure of the spread of the data. And if the normal distribution is supposed to tell us something about data, ultimately, I'll explain more about that in a minute, then I can say it tells me how spread out the data is or the curve is. So just think about it like this. The far edges of the curve are 3 standard deviations for the mean. The bigger the standard deviation is, the further the edges of the curve are from the middle. Okay, so a curve that's wider is going to have a larger standard deviation, and a curve that's narrower is going to have a smaller standard deviation. So even though I can't really get any numbers from this very well, curve C appears to be the widest and therefore has the greatest standard deviation. Okay, all right, now let's talk about data, because you know we're in statistics class, and part of what we do in statistics is we describe data, make inferences from data, and so on. So things that tend to be normal are often things that you can measure about people. Okay, so how tall people are, how much they weigh, and so on. And here's an example of I took the weights of 3 million newborn babies and tallied the data, and we have this normal distribution to describe it. All right, so when I look at this, here's what it seems to tell me. Okay, it says the mean weight of a newborn is about 3,300 grams. Okay, that's the point right in the middle. All right, so that's almost it's like saying the average weight of all these newborns is about 3,300 grams. Okay, so we newborn babies, 3 million of them, we weigh them all and we find the mean, and it's about 3,300 grams. Now, we said that if we go back up here, this point that marks off 1 standard deviation above the mean or below it are these inflection points. And I said if you can look at this, maybe you can just eyeball this and you don't need me to describe it, and that's fine. But if you look at this straight part right here, where it's not curved like that or curved like this, the straight part, roughly the middle of that is where the inflection points are. Okay, it's not necessarily marked on the graph, but when I look at this, it's it wouldn't be out of the question to think there's the inflection point. So this is 1 standard deviation above the mean, and there's the other one, that's 1 standard deviation below it. So what's the standard deviation then? If 3,300 is the mean and 3,900 is 1 standard deviation above it, then how far is that? That's 300, from 3,300 to 3,900. So 300 would take you 1 standard deviation up. Okay, and then, 600, sorry. 600 would take you, whoops, I messed that one up. 600, all right, so 600 would take you 1 standard deviation up, and 600 would take you 1 standard deviation down. 3,300 take away 600, that's 2,700. Okay, so we can say the standard deviation is 600 grams. Now, what other inference could we make about that? Well, there are these other percentages on the spread of the data. We could say 68% of the curve or the data is within 1 standard deviation of the mean. 95% within 2, 99.7 within 3. So I'll just take that first one, 68%. I could say 68% of the newborns weigh between, so what's one standard deviation down and up? 2,700 and 3,900. Okay, so that's an inference I can make from the curve. 68% of the newborns in the study weigh between 2,700 grams and 3,900 grams. So I can make an inference about the spread of the data. Okay, so the standard deviation is 600. That's how far up and down from the mean you go. All right, to get here and here, but then those numbers are 2,700 to 3,900. Okay, real quick. Well, let's look at MyMathLab. Okay, so here's the questions I want to talk about. Let's do this one first. Question 2. Where it says, determine whether the following graph can represent a variable with a normal distribution. Okay, so I'm looking at it here. Explain your reasoning. So when I look at this, it's symmetric. Like here's the middle, okay, and it looks the same on each side of that, so it's symmetric about the mean. And then I'm taking the inflection points here and here, okay. So it doesn't seem to cross the x-axis. I don't see the curve going underneath the x-axis, okay. So I'm just like mentally I'm going through this checklist, like is it bell-shaped, is it symmetric, it doesn't cross the x-axis, and so on. So yeah, I can agree with all those things. So it's not skewed right or skewed left, and I'll explain what that means in a minute. It doesn't cross the x-axis, so yeah, it fulfills the properties of the normal distribution. What about the mean and the standard deviation? Okay, so let's look at it a little bit closer. The mean would be the middle, so that's right here. That's where this peak occurs. That's where the middle is. It's symmetric on either side of the mean. If this is 15 and that's 20, then this is 17. Okay, so then I got the middle right there at 17. So the mean is 17. And then I said the standard deviation is about 2. Okay, well, let's see. Here is the inflection point, all right? And here's the other one. And what is that? So here's the straight part right here and here. And about the middle of the straight part, that's where the inflection point is. That takes me right there. So this is 17, 18, 19. That's where that appears to be. 17, 16, 15. That's where the other one appears to be. So I would say that it appears that the standard deviation is 2. Okay? So this point, in other words, is 1 standard deviation from the mean. But how far is that? 1, 2. That's how far it is. So the standard deviation is 2. This point is 1 standard deviation below the mean. How far is that? Well, this is 17, 16, 15. It's 2. So here's the first inflection point, 2 up. That's 1 standard deviation. Here's the other one, 2 down. That's the other standard deviation. All right? Or that's the other inflection point in the standard deviation. That's why I say that the standard deviation is about 2. That's how far above the mean and below the mean you have to go to find the inflection points. Okay. Now, let's go real quick and talk a little bit more about symmetry. A normal distribution is symmetric about the mean, right? So I've illustrated that with the graphs I've showed you so far, as opposed to being skewed, okay? So to be symmetric means if I drew a vertical line down the middle where the mean is, the graph of the distribution and the resulting halves are mirror images. Okay, so we talked about that. So a normal distribution is symmetric. It's not skewed. So we could say a distribution or graph would be skewed to the left if its tail extends further to the left. So it's not symmetric. The tail goes a little bit further to the left, and skewed right if the tail extends to the right. So let's see an example of that. So this one, you see how it's not symmetric. It's not a mirror image of itself in the middle. If you could find this peak right here. The tail is much bigger on the left than it is on the right. So that would mean that, okay, on one hand, it's not a normal distribution because it's not symmetric. There's no middle that you could say it has a mirror image of itself on either side. It's not bell-shaped. But the tail extends further to the left, so it's skewed left. Okay? All right, so this one's not normal. And let's look at one more. So this one does look symmetric and it does look bell-shaped. Okay, so it's got that going for it. But as far as it being normal, yes, it's symmetric, it's bell-shaped, but the normal distribution kind of bends down towards the x-axis but never touches it or crosses over. And this one, like, very obviously crosses over the x-axis, and the normal distribution doesn't do that. All right, so this graph is not a normal distribution because it crossed the x-axis. Okay, now, so there's some examples on the basic properties of a normal distribution. I didn't do any problems in this video. I didn't do any calculations or anything like that. That will occur in additional videos that come after this and problems in the assignment that are beyond the ones I showed you. But we start with knowing what the normal distribution looks like and how to recognize it.